Okay, we're going to continue on with our integral unit today. So in our last lesson we looked at antiderivatives. So today we're going to do the same thing, but we're going to use the integral notation instead. And then we're going to learn how we would apply the chain rule backwards, and we're also going to figure out what a definite integral is. So to start with, let's just get used to the notation. So yesterday when we did antiderivatives, we would take some sort of starting derivative equation. So let's suppose it was 3x squared. So when we did the antiderivative, we would raise the power and divide by that new power. So in this case, that would simplify to x cubed. And then remember, we needed a plus c because it could have a constant. So we're going to do the same thing, it's a different way of writing it. So the integral notation, you can see what we just did with the antiderivative is this part right here. So we took our original, raised the power by 1, and then divided it by that power. So with integral notation, we're still doing the same thing, except it sort of looks different. So the little s symbol at the beginning is integral, so it's saying find the integral of x to the negative 4, or in other words, find the antiderivative of x to the negative 4, and the dx at the end. It's just like when we write, if we were doing a derivative and I gave you a y equation, we would calculate the derivative with respect to x if it was an x variable, or we could do with respect to t if we were doing a rate, and then we'd times it by dx dt or something like that. So on the bottom of the derivative, that told us what variable we were doing with respect to. With integrals, it works the same. So this is just saying with respect to x. That's just telling us what variable we're going to do the integral for. Other than that, it works the same as antiderivatives. So for this first one, we would raise our power from negative 4 up to negative 3, divide by that new power, plus c, and that's it. Second one, you can see it's the integral of 1 over 4th root of x. So the first thing I would do is change that to a fraction. So that would be x to the negative 1/4 dx. And again, we don't care whether the dx is there or not, really doesn't make much difference, other than it's telling us to do our variable with x. So now we'd raise our power, so negative 1/4 plus 1 would give you 3/4. We divide by 3/4, but it's simpler to write it as multiply by the reciprocal, so that would be 4/3. And that's it. So integral notation works the exact same as antiderivatives. So here's a couple more, and they're basically still the same, just we have a number in front. So let's actually make it a little bit more complicated. Let's change this question to be 4x squared plus 3x minus 7. So it doesn't do anything different, we just have more than one term. Sometimes you'll see it with brackets around, and that's just to help you separate the dx away so it doesn't look like it's 7 dx, which can kind of sometimes be confusing. So whether there's brackets or not doesn't make any difference. Raise our power to 3, keep the 4 there, divide by the new power. For the second one, raise it to a 2, divide by 2, raise the 0 to x to the 1, put on our plus c, and we're done. Okay? So whether there's one term, more than one terms, really doesn't matter, just apply the power rule each time. So this bottom one, raise it to a negative 2, divide by negative 2, and in this case we can simplify that a little bit better, and we're done. So basic power rule, everything's exactly the same like we did yesterday. When it comes to trig, we looked at some basic ones in the previous lesson, but we can actually do any trig derivatives. So as long as they're one of our 6 backwards derivatives, we can still apply the same integrals. So when you see something, especially these bottom ones, when you see something like cosecant times cotan, you might think, hey, that's a power rule situation or a product rule situation, but we don't have to worry about it because we know that working backwards, the derivative gives you both of those. So identify trig ones if you can to try to match what's on the formula sheet. And remember, we can do identities. So if I gave you something like 2 sine x cos x, it doesn't match any on the formula sheet. It would be a product rule type of situation, which we want to avoid. So if we use an identity, we could change this to sine 2x. Now we're just basically doing a regular derivative. So the only thing, or regular integral, the only thing that changes is we would keep the 2x, and we could put brackets around there to make it a little bit better, but we'd do the integral of sine, which would give us negative cos, keep the brackets the same. But remember with chain rule, and this is going to lead us to what we're going to do today, with chain rule we'd always multiply by the derivative of the brackets. So in this case we just have to divide it by the derivative of the brackets. So if you do have those extra numbers, follow the same logic but divide. Okay. If you get a question where you start seeing different powers like cubes or fours or something, then we're going to get into our chain rule situation. So we'll look at that in a bit more. So remember with chain rule, when we're doing a regular chain rule question, let's just do an example. So let's suppose I gave you something like 3x squared plus 5 cubed. So remember our order was we brought the power down, so we brought the 3 down first. Then we would drop the power by 1, so that would make it to a 2. And then we'd multiply by the derivative of the inside. So in this case the derivative of the inside is 6x. So then we would simplify that to make it 18x times our brackets. So that was doing our regular chain rule forward. The chain rule in reverse works the same, and we actually call it integration by substitution, because it's sort of like when we did chain rule, we'd call whatever's in brackets a u, and then we do du dx times dx, dy dx, and all those kind of things to try to get it to work. So it works the same, but it's probably more confusing to do the substitution than it is to just follow the same process we did above, but do it backwards. So let's do the same question down below to sort of see how it would look. So if we start with our answer, this is what our question would look like. So you can see our brackets is the f of g part, and then the derivative, in this case, simplified, would give us 18. Once we put the 6x with the 3 and all that, we simplified it, we just got, oops, it'd be 18x, I forgot the x. Okay, so that's our derivative and the original sort of mixed together. So now we're working backwards, we do the exact same thing we did with power rule, but we would do it in reverse. So the first thing we want to do is keep it the same. So keep the 18x part the same. We're going to raise our power. So we'll raise the power to a 3, divide by 3, and just like we did with derivative of the inside, we multiplied by the derivative of the inside, so in this case we're going to divide by the derivative of the inside. And you can see now when we simplify that, the 18x on the top, 18x on the bottom would cancel, and we would get the exact same as what we started with, other than we have to put on the plus c. So working with the chain rule backwards, and like I said, I'll just call it backwards chain rule instead of integration by substitution. It's just an easier way to see it. And you kind of remember, if you remember the forward direction, working backwards is a little bit simpler. So let's do a few examples of this reverse chain rule. So again, remember we don't change what's out front, and we basically ignore it because it should cancel out once we do our derivatives. So we keep the front the same, keep our brackets the same, raise the power to a 9, and then remember we got to divide by 9, and in this case our derivative of the brackets is 2x, so we also divide by 2x. So I typically just write it like I did, where I just put it as a one big fraction out front, and then we can see the 2x's would cancel, so our final answer would be 1/9 times our brackets plus c. And that's it for that one. The second question, I would first of all get rid of the square root. Let's write it as brackets to the 1/2. And now we can follow our chain rule. So we'll raise the power. So raise it to 3/2. We have to divide by 3/2. We'll write that as 2/3. And we have to also divide by the derivative of the inside, which is 4. So that would give us 2/12, or we could simplify that to 1/6. And that's it. So remember with any kind of integral, we could always do the derivative to make sure it works. So if you weren't sure you did this right, do your regular derivative step and see if it turns back to the original question. Okay, the bottom one works the same. Let's keep the front unchanged. Raise our power by 1 to 3, divide by 3, and our derivative on the inside is 6x squared, so that would also be divided. So you can see in this case the x squareds cancel and the 3's cancel. So we just end up with 1/6. For a chain rule to work in reverse, those x's out front, if there are any, they have to cancel. If they don't, the chain rule doesn't work. So for example, if this was an x cubed out front, we wouldn't have been able to cancel all of them, and you can't just leave the x there. Because if we were to go the other direction, that would turn into a product rule, which would give us a way different question to start with. So we will get into that, but that'll be more of a product rule situation, and we'll worry about that a little bit later on in the unit. So for now, anything that has a number in front, it should cancel. If it doesn't, something's wrong. The chain rule isn't going to work. So quick review. Remember with the chain rule, to apply it in reverse, you want to add the power first, divide by that power, and then also divide by the derivative of the brackets. That's really the only extra step compared to a power rule. So if you got, let's look at a couple more examples. So if I gave you something that had, let's say it was x, let's do integral. I don't know why I'm writing it like that. Let's clear that off. So let's say do the integral of x times x minus 5 squared. So it looks like it's a chain rule, so let's try it. Keep the x the same, raise the power to a 3, divide by 3, divide by the derivative of the inside, which is 1, and people would say, oh, there's my final answer. But again, if we tried to do the derivative, it doesn't work because this is now a product rule situation, so we'd have to do like a f times g situation, which is not going to work. It'll give us a way different answer. So this one, we can't do the integral yet. It's not a chain rule situation. So we'll leave that type till a little bit later on. So like I was saying earlier, these x's out front have to cancel for a chain rule to work. Okay. The other one that sometimes causes issues when we deal with trig, so let's look at something like cos x times sine cubed. So that almost looks like it's another product rule situation, but with trig, often because the derivatives are similar to each other, if we treat it like a chain rule, it should work pretty good. So if you rewrote this question so it looked like that, now we can just apply the chain rules to the brackets. So let's leave the cosine the same. We'll raise our power from sine cubed to sine to the 4th. We need to divide by 4. And we also need to divide by the derivative of sine, which is cosine. And that should be it. So you can see with this one, our final answer would be 1/4 sine to the 4th. And we can rewrite it back with the 4 on the inside. And that would be our final answer for that one. So with trig, just try to think of it, if you get multiple trig, try to write it or rearrange it into a chain rule type situation. And those tend to work pretty good. So our last topic today is how to do a definite integral. So what looks different with a definite integral, it'll start looking the same. So you'd had something like, let's suppose we have integral of 4x dx. So we already know that that answer would be raise it to 2, divide by 2, so that would give us 2x squared plus c. So that part's still the same. The difference now is I'm going to give you a specific interval for the domain. So we're going to say we're going to only want to calculate this integral from, let's say, -1 to +3. So you'll see the little numbers written at the top and the bottom of the integral sign. And what that means is we actually do the antiderivative, but we need to plug those values into our equation to calculate a number answer. So similarly to what we did before with derivatives, once we had a derivative, we could plug an x value and that gave us the slope. It works kind of the same working backwards. I'm giving you the equation, we're going to do the antiderivative, we're going to plug in two x values and subtract those two answers. We'll start looking at what that means tomorrow, like what does it actually mean, how does it apply, but today let's just figure out how to do it. So we don't do anything different other than we take our antiderivative and we usually rewrite it with square brackets and we just put those numbers in the same spot. And what this means now is take the 3 and plug it in. So if I do that first, I would have 2 times 3 squared plus c. And then we're going to subtract, let's put brackets around that. Then we're going to subtract the -1 plugged in. So that'd be 2 times -1 squared plus c. and we subtract those two answers. So the nice part is you can see the c's cancel, c minus c cancels. So with definite integrals, we actually don't have to worry about the c. It's always going to cancel anyway. So all we have to do is worry about the numbers. So in this case, 2 times 3 squared would be 18. 2 times negative 1 squared would just be 2. Subtract those two answers, and we get 16. Your calculator will do this. So I don't have the calculator app on here, but I'll show you in class. But you could always graph the original equation. So in this case, graph y equals x to the fourth. Go to second calc and choose number 7, which is the integral button. And then it asks for the lower value, so put in an x of negative 1. It asks for the upper value, put in x equals 3. Hit enter, it'll give you the integral as being 16. So your calculator will do definite integrals, but that's about all it can do. So kind of like with slopes, it's a little bit useless, but it does help for these kind of questions if you want to try it. The thing to remember is you put the original equation in, not the antiderivative. Okay, so let's try a couple examples. So this one I've got some notes with it, but we can kind of cut to the chase. So here it's saying calculate the integral of x cubed from negative 1 to positive 2. So we need to do the antiderivative. This function is continuous, so we don't have to worry about asymptote lines or breaks in the graph. We'll start worrying about that tomorrow. So what we want to do is take this graph and do our antiderivative. So I've got it written down below. The antiderivative would be 1/4 x to the fourth. And now we want to substitute 1 and 2. Remember, we don't need to worry about the plus c because they'll cancel anyway when we subtract them. So all we need to do is plug in a 2. And then we need to subtract the negative 1 plugged in. And that's it. So do that math, and you can do it in your calculator if you need to, but 2 to the fourth is 16, quarter of 16 would be 4, negative 1 squared is 1, so in this case we get 4 minus a quarter, so we'd have 3.75 or 3 3/4, or however you want to write it, doesn't really matter. So that's it. So this fundamental theorem of calculus is just a rule to say take an integral, plug in the two values, and subtract your answers. The order does matter, so make sure you don't put it in the other way around. Like if you went negative 1, take away positive 2, it would give us a negative answer. And we're going to see tomorrow what that actually represents. So always do the top number minus the bottom number. Okay, here's another one that's a little bit more complicated. And we could have more terms, it doesn't really matter. I'm just showing you one term just to give you the idea. So for this one, I rewrote the 1/3 cube root of x squared as x to the negative 2/3. So if we do our antiderivative, we would add 1, which will make it positive 1/3, divide by 1/3, which would be the same thing as multiplying by 3/1. And we're going to do the integral from 1 to 8. So plug in an 8, subtract the 1, and let's solve those answers. 8 to the cube root is 2, so 2 times 3 is 6, minus 3. Our final answer for this one will be 3. Okay, so pretty easy question. And I have one more. So here's a trig one, and they work the same. You can see I've already done the first step, so the antiderivative of sine is negative cosine. We're going to go from pi to 2 pi, so all we have to do now is solve this. So we'd have negative cosine of 2 pi, subtract negative cosine of pi. A little bit trickier because we're dealing with radians and unit circle stuff, but remember 2 pi is the same as 0, and that coordinate would be 1, 0. Pi is over here, and that coordinate would be negative 1, 0. So if we plug those in, we'd have negative cosine of 2 pi, which is 1, minus cosine of pi, which is negative 1, and you can see the double negatives. I guess I could have done it right at the beginning. The double negatives would have made it plus, so we have negative 1 plus negative 1, which would give us negative 2. And that's it for today. We're going to extend this tomorrow, so if we were to look at this graph on your calculator, remember our sine graph would look something like that. And what we've just done is gone from pi up to 2 pi. So we're going to talk a bit tomorrow what does these things actually mean. So a little bit of a hint is that actually gives us the area under the curve. So your calculator, if you draw it on your calculator, it actually shades in this section of the graph So the negative 2 is actually representing how much of that graph is below the x-axis, between pi and 2 pi. So that's going to be our first application we look at with integrals. And that's all for now.